In this video, we're going to talk about this more linear algebraic stuff on the solutions of linear equations. And the kind of fundamental part of this whole story or theory is this existence and uniqueness of mth order linear equations. So proving this one requires, in general, integral techniques and some of the real analysis and advanced calculus languages. But once we assume that much of a heavy-duty work here, rest the part comes nicely and in terms of linear algebra. Although in general we have mth order linear equations, it's introduced in the usual textbook, we're going to mainly focus on m equals 2, the second order linear equation, or third order linear equation. And by just looking at the examples of m equals 2 or 3, I think it gives you a good idea about what's going to happen to the higher order linear equations, and what's going to how these examples extend to the higher order. I think it's pretty clear. So we're going to focus mainly on m equals 2 or 3. So the general shape of the linear operator associated with the second or third order linear equations will be this one. This is the second order operator. This is the operator associated with the third order equations. So first, the important theorem is that if you look at the homogeneous equation of this operator or these equations, the dimension of the solution space, which is the same as the kernel of L, those space of function, collection of functions, if you applied it here, it becomes 0. That's the kernel. The dimension of that, it's m. So if it's a second order, that's going to be dimension 2. If it's a third order, it's going to be dimension 3. I always prefer stating the theorem not just like simply like this with a more specific information, but sometimes that's not a good idea, but I think this time is a good idea. So I'm going to tag it as a remark. And how is this, what is the outline, what is the detailed setup that allows us to conclude like this is the following. So what the existence and uniqueness theorem says is that if you give initial condition on the value of a function and the derivative, for the case of the second order, there's only one function that have that condition. So for example, if I'm thinking about a particular function yx, if you have a function such that, st, that it's a kernel of that function, it's a 0, if you stick this one into, so this is the case where m equals 2, forgot to mention that here, m equals 2, then y1 will go in there, y1 prime, so let me write that here. So this part here is y1 double prime px and y1 first prime qx and y. This thing set equal to 0. And there are many functions that has this property, but if you add the condition y1 at some point, usually this solution set is talked about locally at some point a, for example, and that was 1. If I just choose this particular function, and the second point is 0. If I put this initial condition, I can put 0, 0, or 1 and 1, or 2013 and 2014. Whatever number you put it in there, there will be one and only one function that satisfies this differential equation and these two initial conditions. So if I put it like this, there will be a unique function that does this job. And we're going to let y2 be a function such that this also satisfies the differential equation, but this time it's a slightly different initial condition. So this second function satisfies the function value 0, but the derivative value there is 1. So it's a slightly different initial value. So you chose these two things. So it turns out this function y1, y2 are linearly independent over constants, and these two things makes the entire kernel, using the linear combination of these two y1 and y2, you can cover all the functions in the kernel and all the solutions of homogeneous equations. So let's go ahead and state the case where m equals 3. Then we have a similar statement, but initial conditions are the first derivative and function value and first derivative and the second value. Those three conditions fills up a three-dimensional space. So here in this case, we can write it like this. All three functions we're looking at is all satisfy this differential equation. So i.e. the differential equation this time is m3, so it's yk, whatever the index you're looking at, the third derivative, and p is a function of x, and yk second derivative, q another coefficient function, and first derivative, and r, yk, 0. So these three functions satisfy all these conditions, but they have different initial conditions. So first, if you look at y1, at the central value at 0, it's going to be 1, and rest of the derivative value is going to be 0, like this. The second derivative here. And if you look at the second function, and it is different combinations, so I'm just going to write that down. For example, the condition for the second function will be like this. Function value is 0, but derivative value is 1. Second derivative value is 0. Okay, the third will be these two things are 0 and that thing is 1. So like this, if you put these distinct, different linear initial conditions, there will be a unique function for each of these conditions. So there is a uniquely defined function y1, y2, y3 that satisfy all this condition. These are all from the existence and uniqueness theorem. That guarantees that there's one and only one function that have this property. Okay, so once you set up like this, and then if you're looking at the dimension and stuff, I'm assuming that you know a little bit of linear algebra. Other than that, none of these things will make sense to you. So you can actually go ahead and prove this statement using this condition. These two y1 and y2 happen to be the basis of this space, the kernel, and this y1, y2, y3 I wrote down in this specific version is the base of these functions. Sorry, not function, not this space here, these form a basis. So let me make another additional comment or remarks about this case m equals 3 here. And the remarks goes exactly the same for m equals 2. I'm just doing that for m equals 3 case. That all the functions inside here, all functions, let me write that statement. So in m equals 3 case, all the functions inside that kernel, this is what we wanted to know. Although the linear algebraic statement is, the dimension of this one equals 3, but I think the following statement is more useful in practice. So how is these functions in the kernel actually look like is in the form of the following that uses this y1 and y2, y3. So namely like this, all the functions look like this, c1 y1 plus c2 y2, c3 y3, where this c1 and c2, c3 are constants. All right, this is a statement that these three functions works at its basis, and if you know linear algebra, this is the statement that proves this one, and together with the linear independency. But let me just explain this one, and this part will make sense. Those two who don't know, don't remember everything about the linear algebra in here. So all we wanted to establish is all the functions in here look like this. That's a pretty good statement. First, we start with a let f be an arbitrary function. Sorry, I had to move out a little bit. Let f be an arbitrary function inside the kernel, and we want to kind of argue that this can be written in terms of y1 and y2, y3 like that. We call it linear combination over constants c1, c2, c3. The trick is that this is a function, and it has this value at that central point. fa is going to be some number c1, and f2, the prime, the derivative, c2 is going to be the derivative value, and c3 is going to be the second derivative value of that function. So since it's a solution to that order 3 equation, so we will be able to compute all these three values, C1 and C2 and C3. Now that's the number associated with this function f, and we're going to compare this one with this function that we're looking at here. So we usually start with a notice that this function we're going to call z, which is a c1 and y1, dot dot dot, that's c3, y3. That function we're looking at here with this number coming from this c1 and c2, c3 coming from this f here. It turns out this function has exactly the same value with c function and derivative value and second derivative value. That's what we're going to check. Notice that if we write it like this, then z of a, so I shook a little bit, I wrote everything in there. So ZA, if you remember the y2 and y3, those having the function value 0, and y1 was the only function that has function value, non-zero value. So let me show you that. So here's the initial values that define y1, y2, y3. If you look at the function value, the only function has non-zero value is this y1, is 1, 0, 0. These are the function values. So back here, so that only picks up 1, and these two picks up 0, so that's exactly C1. So this function that we're looking at happen to have a same function value at A. So let's look at the z prime of A. Then these are constants, and y1 and y2 and y3 are differentiated. If you look at those values, y2 was the only function in that three functions that has non-zero first or derivative value. So this becomes 0, and that becomes 1, so C2 picks up, and that becomes 0. So this function we're looking at happen to have the same derivative value. So let's look at the second derivative value in that list that I showed earlier, and in the second derivative, y3 is the only function that picks up a non-zero value. So that picks up C3, and these two values, because y1 double prime, y2 double prime was 0, that picks up like this. So the function we're looking at here happen to have exactly the same initial condition, C1 and C2 and C3 there. So it is the existence and uniqueness theorem that guarantees that if you're looking at a function in the kernel, something that you have to argue that this is actually in the kernel, this in the kernel, and have the same exact initial condition, then you can guarantee that this function, C1, Y1, and C2, Y2 plus C3, Y3, with the same initial condition, must be the function that you pulled out arbitrarily from the kernel. So that kind of proves that everything is, the function is in this form. So you can easily argue that any function in this form with arbitrary values C1, C2, C3 will be in the kernel of this operator. That's simple consequence of immediate consequence of the linearity of this L here. So I wrote it in non-linear algebraic terms or in context, but in fancy language, what this says here is in linear algebraic term is the dimension of the kernel is 3, because this y1, y2, the three function there are that generates everything in here, and these y1 and y2 and y3 are linearly independent. That means you cannot come up with a smaller number of functions like 2 or 1 can do the same thing. So you can generate all the function over the constants.